Then let's talk about the semaphore implementation. So when we want to implement the semaphore, we have to ensure no processes execute wait operation and signal operation on same semaphore at the same time. Otherwise, we will get into trouble. So basically, there are two options to implement the semaphore. The first option is directly to implement the semaphore by busy waiting, so which is very similar to spin lock or mutex lock. So therefore, it has the same pros and cons as a mutex lock. For the advantage, it can provide a very good responsiveness. So whenever the semaphore is available, the waiting process can immediately grab the semaphore and to be executed on the CPU. However, the downside is that this option will waste CPU resources since the waiting process needs to keep spinning on the CPU, especially when one application spends a lot of time in critical section. Other processes who are waiting for the semaphore, they will be there waiting in the CPU for a long time and waste too much CPU resources there. On the other hand, another option is to place wait option and the signal option code in the critical section. So for this option, we will use the busy waiting to protect the critical sections where the wait and the signal codes are located. So since the wait or signal code is short, so therefore it won't bring too much overhead to the system. In this slide, we are going to implement the semaphore by second option. So where the wait signal code is placed in the critical section. To avoid busy waiting within the wait and the signal operation, so how to achieve that? We use a waiting queue, which means associated waiting queue with each semaphore to avoid the busy waiting within the code of a wait and the signal operations. Then we redefine the semaphore as shown in the slide. So beside the integer, we have another linked list which pointed to a list of PCBs. So with this list, it can help us remember which processes are waiting on the waiting queue. To associate with this waiting queue, we have two operations. One is block, which places process in appropriate waiting queue and waiting for the semaphore. Another operation is wake up. So what the wake up does is that to remove process from waiting queue and place it into ready queue. So as long as the CPU is available, if the process has been chosen by the scheduler, the process will be placed on the CPU and get executed. So we extend the semaphore with a linked list to record the processes who are waiting for the semaphore. And then we learn how we use block and wake up to put and remove processes from the waiting queue so that they can be executed on the CPU appropriately. This slide shows us the pseudocode of wait and signal operations so that we can know how the wait and the signal operations are implemented in real world. And remember that both wait and signal operations are put in the new critical section and protected by busy waiting. So when a process gets into a new critical section where the wait operation is located, the wait function will be called and passing the semaphore. So instead of using the while loop, the new wait operation will decrease the semaphore integer value by 1. And then to check if the integer value is less than 0 or not. If yes, means no more other processes can be beyond this point. They have to wait. Then add the current process to the waiting queue. At last, call the block function. Remember what the block function does is to place the process into the appropriate waiting queue and take the process out of the CPU and wait there. So later, when another process is executed the signal operation with the same semaphore, it will increase the integer value by 1. And also, if the integer value is less than or equal to 0, so one process can be removed from the waiting queue or the linked list and wake up this process with a wake up function. So which means the process can be removed from the waiting queue and put onto the ready queue. So as long as the CPU is available and the scheduler chosen this process, so this process can be put on the CPU and continue to make a progress. So if you look closely to the integer value, the absolute value of the integer value is equal to the number of processes. So waiting on the waiting queue, for example, at the very beginning, we set the semaphore as 1. So when a process executes a wait operation, after decreasing the integer value by 1, the semaphore is 0. So under this condition, the process won't be blocked and put onto the waiting queue. So later, another process called the wait function, the semaphore becomes -1, and the process will be put onto the waiting queue and be blocked. Then one more process called the wait function, so semaphore will becomes to -2, and this process will be put onto the waiting queue and blocked as well. Then currently, the integer value is equal to -2, and the two processes are put onto the waiting queue now. Then one process called the signal function, and semaphore is becomes to -1. So one process will be removed from the waiting queue and waked up. So on and so forth. According to the aforementioned example, so you can see that the absolute value of the integer is equal to the number of processes currently on the waiting queue.